Hello class, and welcome to our first flipped classroom. I gave you this worksheet today in class, so you'll need to get the all about tangent lines out. And you'll probably need to pause a few times to write stuff down or to try things yourself so that you get practice as well. I'm trying to keep this as short as possible, so I'm going to not necessarily show all my steps or kind of move quickly. So just pause and rewind anytime that you need to. So the first thing, though, you should do is read through this first page. It kind of talks about what a tangent line is, and you should have talked about tangent lines in geometry, but we're going to do them to curves on a graph. And so if you look at the graph, the main things you need to make sure you know is this main definition, that a tangent to a curve at a point is a line that best models or approximates the behavior of the curve at that point. And the other main thing on this page you want to know is this definition of a tangent, that a function at x equals a has two things in common, the point of tangency and the slope of the tangent. So this is an example of a curve with a tangent. They share this point, and then the slope at that point is the same for that line and for the curve. So please kind of pause or at some point read through this to explain, to learn a little bit more about tangent lines. So the first thing you're going to do is sketch tangent lines to the function at the labeled points. And so it's best if you use a ruler. And how you do a tangent line is you pretty much take a ruler and kind of put it against the curve so that you're going to intersect that point and then draw a straight line. And so you should mostly intersect at that point, and the slope at that point and the slope of your line should be the same. So the only place it needs to intersect is that point. And so I drew the tangent lines at the different points on these four figures. So again, pause to draw them in. And then after you draw them in, we're going to answer these questions. So you might want to pause and kind of think about them first so that you can see if you understand what we're doing. So they said the position of a tangent line depends on the concavity of the function. And look at 3 through 6, complete the statement. So just to review, concavity means if it's curved upwards or if it's curved downwards. If it's curved up like this, we say it's concave up. And then if it is curved down like this, we say that it is concave down. And those are two terms we're going to use a lot this year. So we need to make sure that we know those. So if you look where the curve is concave up, if the tangent line, does it lie above or below the curve? So if I look at my figures, the only one that is concave up everywhere is figure 3 because it's a parabola shaped up. And so if I look at point A and C, my line is pretty much below the curve everywhere. So we're going to put in our first blank, where the curve is concave up, the tangent line lies below the curve. Except at that point, because then it's on. And then if I look at concave down, so that would be figure 4. The tangent is, you can see at each point, it is above the curve. And then at a max or min, or a turning point, there's two things we can say about a tangent. So if you look at figure 3 and 4, here at B and here at B, we have a turning point, a max or a min, and there the tangent is horizontal. So that's one case. And then the other case is that this is called a cusp, which we'll learn about in a few classes, but a sharp turn is another place that you have a max or a min. And we usually say that the tangent is non-existent because there's multiple, because I could draw one here with a slope of 1, here with a slope of -1, one with a slope of 0. So we're not really sure which one would work. So we usually say it's non-existent since there's multiple. And then a point of inflection, right, just in case we don't remember, a point of inflection, which we write a lot of times as PI, is where the graph changes concavity. And the only place that happens is on figure 5. If we look at point P, my graph was concave down, and then it switched to concave up. And so at that point, the tangent ends up being both above and below the curve because it goes through it, and then on the concave up part, it's below, and on the concave down, it's above. And then the next one, at a point on a linear function, we can see at A and C on figure 6, it's a linear function. The tangent is the exact same as the function. Okay, they're on top of each other. And then the last one is a sharp point, and that tangent, again, we say is non-existent. Okay, since again, there are multiple. So I would just pause for a second and kind of read back over that and look about what tangent lines are and if they're above and below for a minute. And then when you're done, you can read this bottom part. So we're going to mostly write equations of tangent lines in point slope form. And this is the equation for point slope form. In Algebra 1 or Algebra 2, you might have wrote it more like this. And the ones are a little subscript. So I fixed it here as a subscript. This is the point slope form you might have used before, but generally in calculus we get y by itself, so we add the y1 to the other side. So we're going to use that to write tangent lines because it's easier than y equals mx plus b, because we don't have to solve for b. So on the next page, we're going to do these 3 problems. So it says in the spaces provided below, write an equation in point slope form for each tangent line that you drew in figure 4. Substitute the point of tangency for the given point. To estimate the slope of the tangent, find a second point on the tangent line that is reasonably far from the point of tangency, and then apply the slope formula. So I'm going to do A, and then I'll let you guys try B and C. So if you go back to the page before, and if I look at A on figure 4, I have this line, and I extended it, and it goes through this point A, which is -1, -2, and then my line also goes through point 0, 2. And it's okay if yours is a little different because they're estimates, but it should be somewhere close. So I'm going to find the equation of this line in point slope form. So to do that, I first find the slope. So to find the slope, I do y2, which I did here, minus y1, all divided by x2 minus x1. And so these are my 2 points, and I did my slope formula. And if I simplify that, we get 4/1. So my slope is 4. And so then all I have to do is plug in my values. So I'm going to do y equals my slope, which is m. And then you do x minus x1. We're going to use point A, which was -1. And then plus y2, which is -2. And if I kind of fix it up a little bit, I get y equals 4 times x plus 1, and then -2. And you're going to do the exact same thing for B and C. You're going to find 2 points on line B, on the line that goes through B, find the slope, plug it into point slope form, and do the same for C. So you can pause and do that. And then once you're done, we're going to look at this bottom part. So it says, look at figure number 2, part 1. The figure shows an arbitrary function f and its tangent at the point A, f of A. Write an equation in point slope form for this tangent line. So they're talking about the very first figure down here. This figure, and my point is A, f of A. So going back to my question, if we want to write that, okay, we're going to just write y equals, okay, our slope, which we'll use m for now, and then we would do x minus a, and then plus f of a. And you'll learn this today a little bit later, but what we use for m when we talk about tangent lines is called f prime of a, so it's f apostrophe a, and that means the slope of the tangent line. So I'm just going to put that in here so we have the official notation. So this is our equation of our tangent line. You need to know it, so you probably want to like write it on a note card or somewhere to memorize it and study. Then the last things, is it possible for a function to have a vertical tangent? If so, what would the slope of the curve at a point of tangency have to be? So if I have a curve like this that's really steep, when you draw the tangent line, it's going to be pretty much straight up and down. It's going to be vertical. So it is possible. And the slope, if you think of a vertical line, the slope would be undefined because the slope of a vertical line is undefined. And then the second question is, can you write an equation for a vertical line? If so, what form would it take? And we should remember from Algebra 1, the equation of a vertical line is x equals, and we'll call it a for the x coordinate. And then the last thing on here is try to sketch a function that has a vertical tangent. So this would be my example, and this would be my a, f of a. So go back and make sure you do those other practice problems. The rest of this I posted online that you can print it so you don't have to write as much, or if you prefer to write, then you can pause and write it. So our main objective is that you can find the average rate of change of a function given an interval graphically, numerically, or algebraically, and then also that you can find the instantaneous rate of change numerically or algebraically. So we're going to look at rates of change, and that's one of the main topics of calculus. So the first thing is average rate of change, which I tend to call AROC because it's easier to write. So it's these main things. It's the rate of change over a certain time interval. They usually write the time interval as A to B. And one example is average speed, which is the distance traveled divided by the change in time. That would be an average rate of change. So graphically, it's the slope of a secant line. So I drew a curve over here, and this line that I drew through it is called a secant line. And a secant line is a line that goes through 2 points on a curve. So a tangent goes through 1, a secant line goes through 2. And if you find the slope of that line, then you get the slope of the secant line. So if I use these 2 points, B, f of B, A, f of A, then my slope would just be y2 minus y1 over x2 minus x1, which would just be f of B minus f of A, and then it's all over B minus A. And sorry that it's sloppy. I'm using my mouse, which is hard to use to write. So f of A minus f of B, f of B minus f of A, and then all over B minus A. There, that's a little better. So that's the formula algebraically for rate of change, for average rate of change. The second thing is called instantaneous rate of change, IROC. Okay, that is a little bit different because it's not over a time interval, it's the rate of change at a certain instant. So it's a specific time. They're usually going to say, like, find the rate of change at t equals some number. So t equals A or t equals C. The calculus term is called the derivative, and we're going to talk about that pretty much until January. So it's very important that you know the term derivative. Graphically, it's the slope of the tangent line. So that's what that first worksheet was about. Like, it's the curve that intersects the line that intersects the curve once. And algebraically, it's the limit of the average rate of change. And here is the formula for the average rate of, or the instantaneous rate of change. Instead of f of b, we usually put the function, so we have an x in it, so we can factor and cancel. And it's the limit as x approaches a of the slope formula. So there's 4 notations for derivatives, and I'll write them in. Okay, so here are the 4 notations for derivative. The last one is rarely used, but the other ones are used pretty often. So please copy those down, and then we're going to move to the next page. So for our example, numerically, you estimate by picking the closest point to the right and left of the time value and finding the average rate of change or slope. And this is to find IROC or AROC, either one for a table. So this is an old AP question. It's really wordy, so we just really focus on the main thing that they're asking. So it says a metal wire of length 8 centimeters is heated at one end. The table gives selected values of the temperature in degrees Celsius of the wire from the heated end. The function is decreasing and twice differentiable. Estimate t prime of 7. So that's all we really want. Show that work that leads to your answer. So when they say t prime of 7, all you do is find the slope between 6 and 8. And then just remember that the temperature is going to be your y's and the distance is going to be your x's. So to do this, we're going to do 55 minus 62 and then divided by 8 minus 6. And this gives us t prime of 7. Remember, we just said that notation means the derivative or the instantaneous rate of change. And if we solve that, we get negative 7 over 2. And we would just leave it like that. When it says include units of measure, we just put the units they gave us. So we would put Celsius divided by centimeters. And you can put the little degree symbol there. Because we took Celsius on top and we divided by the centimeters. So this is should be an easy AP question that you're able to do. So I want you to read this one and try this one then. So you can pause and do that. And then the last thing we're going to do is this example from page 59. So please pause and read the question first. And then after you read it, we're going to find the average speed of the rock during the first 2 seconds. So they give me equation, y equals 16t squared, and we're doing average. So for average, we're going to do f of b minus f of a all over b minus a. And in this case, my a is 0 and my b is 2 because it says the first 2 seconds. So we started at 0, we ended at 2. So I wrote my formula. I found my A and B over here by plugging it into my Y formula, and then I would just subtract them. So 64 minus 0 divided by 2 minus 0, and obviously that would give us 64 divided by 2, which is 32, and then it's feet per second because we took feet and we divided by second. And then part B says, estimate the speed of the rock at the instant at t equals 2. So for that, we're going to do the limit one, and this is why we did so many limits first chapter. So when we do that one, we have this formula. We do the limit. My A is 2 this time. I'm going to use t instead of x because that's my variable. So I do t approaches 2, my function, which is 16t squared, minus 64 all over t minus 2. And then you would factor out like the 16. And then we get this. And then we can do our difference of squares. So we get 16 times t minus 2 over t plus 2. The t minus 2's cancel. And then we plug in our limit and we get 64. And again, you would do units, which would be the same feet per second because we took feet divided by second. So that's it for the notes. Please try I think it's 3 problems in the textbook that are on the calendar. And then I will see you on Tuesday. I hope you have a great weekend. Bye.